Hello, everyone. Thanks for coming. So yeah, this talk will be about ROS2 on what I'd like to call small embedded systems, and I'll get into a little more of what I mean by that adjective there. So the first question, of course, with any talk is, why do we care? And what I want to say, and the reason we care for small embedded systems is because they're everywhere nowadays. So by that, I mean the microcontrollers nowadays are effectively in every gadget now that has a blinking light on it. Odds are there's a microcontroller in there. So this picture is just to try to show the ratio of microcontrollers nowadays. So that big robot there on the left is a robot we did in collaboration with Sandia National Laboratories and IHMC. And that's a big walking humanoid. So a big complicated machine, person size, person mass. But there's only actually 2 full-on computers on there, so 2 x86 machines up on the very top of the torso. The rest of the machine has FPGAs for high-speed data transfer, but then this gigantic constellation of microcontrollers where all the sensors are. So there's all this data flying around with all these little microcontrollers. Wouldn't it be great if we could standardize how these things talk to each other? And so that then we can write generic tools just like we have in the ROS at the higher level. As if this trend continues in the future, this will become an even bigger and bigger issue as microcontrollers continue to go everywhere. So the second goal would be if we can fit ROS2, or at least some implementation or some client of it inside sensors, now we can get rid of driver nodes because ROS2 can actually run in the sensor itself or in the actuator on the edge of the system. So once we have then nodes, like actual ROS2 clients talking to the system, maybe we can start to push more and more of the real-time processing into the sensors and actuators at the edges of the system. Because modern microcontrollers really are just getting more and more awesome. It's the kind of thing where you go to the trade show every year and they're like, oh yeah, here's this thing and this runs twice as fast as last year. Have a nice day. So that's still happening in the microcontroller world. It's really exciting. And so when we partition these computational units, then we can have their little tiny real-time things, like say, for example, you take a little sensor reading, you have a little bit of pipeline you want to do, a small bit of processing, and then pass it down. It's easier to hook that in when there's a small system. It's just a smaller thing to take care of and to schedule. So embedded systems is a big term. If you ask 10 people what they think embedded systems are, you'll get 10 pretty different answers. So there's kind of 4 worlds I'm going to draw here. So that the left side there, the first column, the 8-bit world, that was made famous by the Arduino and the AVR processors lately. They're pretty small, so this talk can't deal with them. They're too small. So the second column that I'm going to talk about here is the 32-bit microcontroller world. So that's things like the STM32, which is used on the Pixhawk PX4, which we just saw. Those you can actually get on the high end of that class. You can have Ethernet interfaces, then we can just natively plug that in. The last 2, so I sometimes call the third column the ARM A-class. It's like a smartphone without a screen on it. It's things like Odroid, Gumsticks, BeagleBones, those kind of things. Those are, you can actually just run ROS normally on them. And then the last column, I like to call those laptops without screens. Those are things like the Intel NUCs, the small form factor x86s. So all these things can be called embedded systems because they don't have screens on them. But in this talk, we're just going to talk about 32-bit microcontrollers for now. So even within that category, you can divide it into all sorts of different ways. There's things that are relatively small, as in they have few numbers of kilobytes of SRAM. They cost just $1 or $2. And then there's what I'll call big 32-bit microcontrollers. And these are the systems, like we see on the PX4 and many other platforms. They're really amazing computers in their own right. They just happen to exist on a single chip. So some of the constraints we have, though, to deal with, the SRAM is the biggest limitation oftentimes. If you're running from on-chip RAM to keep the board small and light and cheap, you typically have, like on the very top-end chips, you'll have a few hundred kilobytes of SRAM. So that's tricky. And that's actually what most of this talk is about, is how do we deal with getting a general purpose middleware client into something that small. So what happened in the past, what's going to happen in the future, ideally here. So on the left side, this is like the sad column. This is the sad music, black and white part of the infomercial. So with ROS1, there was numerous issues that made it hard to embed. So one of them was the startup sequencing problem. That means that you had to have ROS core up before the clients could connect to it. And that's sometimes a little bit tricky because microcontrollers boot effectively instantaneously. And then, as opposed to trying to connect to a full-on like Linux computer, which is having maybe a multiple second boot time at best, and then it'll fire up ROS core. So that was always tricky. You had to either reset the microcontroller or delay the boot sequence somehow. Even more practically though, XML RPC, which ROS1 uses for negotiation, is just difficult to deal with in highly constrained memory environments. It's a tree structure. It's coming at you in ASCII. You're having to separate this parse tree and buffer everything right. There's been heroic efforts to make that work, but it's just fundamentally a difficult problem. ROSCon also uses TCP everywhere. There is some UDP support, but TCP in general needs some buffering to do with high-performance TCP. You want to buffer the packets that are in flight. And so that can be tricky if you're memory constrained. So then the natural thing is let's use UDP. So that's why there's UDP ROS. But that implementation is, I think it's fair to say, not complete. It doesn't deal with the multicasting, which is one of the big benefits of UDP. And then if you have large messages, you have to fragment them to fit them into Ethernet frames. But there's not support in UDP ROS for sending missed fragments. So if you have a really big big message, like a big image or point cloud, and you drop one of those Ethernet frames, it's, well, you better wait for the next message because you can't recover it. So anyway, embedding ROS1 tends to be difficult. With ROS2, this is the happy column, happy music, like full color, part of the infomercial here. So there's no master node. It's actually a fully distributed system. It's multicast UDP discovery. That just means all the nodes come up and they start sending multicast packets to the network. And those in RTPS, that's the protocol beneath DDS, which is beneath ROS2. It's just a list. It's a parameter list. So instead of this tree structure you're having to parse out in ASCII, it's just a well-defined list of parameters. The RTPS or UDP data streams, they're much more sophisticated than UDP ROS. So you can have all sorts of quality of service settings. You can dial it one way and you can get TCP, where every packet has to be acknowledged. You can dial it the other way and you get effectively fire and forget UDP, where you just send the message on the wire and have a nice day, you move on to the next one. You can also, and more interesting perhaps for robotics, put it everywhere thing in between. So maybe you want to send messages up to a few times, and if it doesn't get there, then you move on. Or maybe you want to wait 100 microseconds. If it doesn't get there by then you move on. So what we're trying to do is showing all these great things. These are great. That's awesome. Let's have them. So what we're trying to show is we can get them with free, portable, small code that we can fit in the on-chip memory of microcontrollers. So to that effect, we've been working for the past few months on a thing called FreeArt EPS, which is an Apache 2 licensed implementation of the RTPS transport, and that's the network protocol beneath DDS, as well as its serialization layer called CDR. So this is a work in progress. I'd say it's like at the proof of concept stage and a little bit beyond, so I wouldn't recommend putting this on your $1 million vehicle this weekend. Might want to wait a few weekends. But, okay, so it's this layered deal. So we can debug this by pointing it towards Linux with a POSIX UDP stack beneath it. But really all it needs is a UDP transport layer. So it just calls functions like send UDP packet. Somebody has to implement that. So you can either point that towards POSIX networking, or you can point it towards a very thin networking stack, which we've written and then targeted toward STM32 and the Atmel SAM-V microcontrollers. And calling our thing a UDP stack is really generous. It just stuffs a buffer and calls it through to the transceiver on the microcontroller themselves. So it's a very thin networking stack. The important thing here is that we really don't need a full DDS stack in order to interoperate with ROS2 nodes. Really what we need to have is the network traffic on the wire that's RTPS packets. So that really opens up the space a lot, because once we realize ROS has its own API, we don't really need to follow the DDS API. Instead, we just need to produce the network traffic that the DDS nodes can understand. So on the left side there is the full ROS2 stack, which we'll have talks more about that over the next few days. It's very elegant API. There's all sorts of template awesomeness so that the code looks very cool and it's all very sophisticated. And you can swap DDS vendors without having to change your source code. There's all these nice layers of abstractions that really help the code look nice. Unfortunately, there's a cost, of course, in memory consumption with stacking those things up. So we're working on targeting that. So instead of having open splice at the bottom, you can have this FreeArt EPS implementation. We're not quite yet to the point where we can fit that whole stack inside of a microcontroller's on-chip memory. So for now, we have this minimalist API there on the right side, which you can write very simple code, which directly calls the RTPS transport functions. So, the API is uglier, it's C-only, but it works. So what's great about this, though, is because RTPS has these buffers which are of known size, the discovery for topics and for nodes, you have a pretty good idea how big those are going to be. And then in the embedded case, if you're writing, say, an embedded node which is going to take inertial unit messages and send them, or a smart camera that's going to send out ROS image messages or something, odds are you have a good idea about what the buffer sizes should be. So you can choose them at compile time and at link time, and that just goes into the executable image. You don't have to have anything on the heap. So these can be all static. Everything's pre-allocated. You're not worrying about mallocs overrunning or anything like that. There are trade-offs, of course. You have to then decide how many nodes can this thing discover. That's the size of buffer you can allocate. But you can make those trade-offs on a per application basis, and this is all open source, so it's easy to tweak and rebuild as needed. So we always start, of course, in middlewares by sending strings around. So the minimal proof of concept here is, can we send an RTPS string from an embedded microcontroller and then catch that on a full DDS implementation with the nice ROS2 API on top of that? So to do that, we've made this talker example. It's all static. Again, no mallocs happening here. It's no dynamic memory, no use of the heap at all. And so this currently takes 100 kilobytes of RAM to run and about 60K of flash. But there's lots of ways we can improve that in the future. This is just the first proof of concept, and we can certainly optimize that later. But that cartoon at the bottom there just shows we have this talker node, which is running either on your POSIX host or on a microcontroller, just bare metal microcontroller, blasting RTPS network packets at an OpenSplice listener, which would then eventually bubble up into the ROS2 space on top. So this thing fits on a single page. This is the full program. I apologize, it's a little bit too much code to look at, but just going through those big bubbles, the call-out bubbles there, the first you see the user allocation. So those are the explicit buffers this is going to use. We're statically allocating this whole thing, so that way we can find out if you have too much buffering going on. If you don't have enough memory, at least the linker will tell you when it tries to link it, rather than you find it later on the line at runtime. So there's some initialization stuff that starts up, and then that second call-out there, we tick the discovery machinery. So that's how RTPS finds these other nodes, this multicast UDP machinery. Essentially, they send out packets on the wire and say, hi, what's your name? Here's my name. Here's how you find me. So that needs to happen on the order of every second or so. And then the last bit, those last 4 lines there, are it's to stuff and serialize the message buffer and then send it out at the wire. So this is the kind of flow of the FreeArt EPS right now on the client side. So strings are fun, but typically in robotics we want to send more than strings. So to do that and to make sure our abstractions are working, we have a few demos here. For the sake of time, I don't have the widgets here on the podium with me, but I'll have them after. We can play around with them during the lunch break or any other breaks during the conference here. So the first one is an inertial unit demo. So that's using one of the popular development boards is the STM32F4 Discovery. You can get that and the Ethernet stack really cheap. So there's a microcontroller on that board. So this demo pulls that pulls the accelerometer at a kilohertz on the board, and then just ships that out over the Ethernet. So that I'll show performance statistics on that in terms of jitter and latency. The next one is a more complicated demo to show how we can make a smart camera with the microcontroller. So I have this also. I'm happy to show that afterwards. It's an image sensor, just a raw CMOS image sensor that wires into a Cortex M7 development board. Then I can barely fit a frame buffer on that, but there is just barely enough room to fit a VGA frame buffer and FreeArt EPS, and so then we can actually send out sensor messages, image messages on the wire. And then on the receiving side of things, so we can subscribe, there's just a LED blinker program, like we always love to build, of course, in computer engineering, the world's most complicated LED blinker, So let's see. So the first demo I'm going to show some performance data on. This is STM32F4 Discovery board. It's been a little bit hot-rodded to use the Ethernet physical layer transceiver and the accelerometer at the same time. There's just one jumper you had to add. But what we're trying to do is to hook that into some lab test bench equipment and get direct measurements of the jitter and latency of this. So as we start running this here, I would wave my hands around, but that's okay. Anyway, on that box where I've circled that in red there, it shows the standard deviation of the time period here. So that yellow trace is the chip select line of the inertial unit, the accelerometer. So when you pull that low, you talk to it, you put it up high because you're done talking to it. Then the green trace shows when we're actually sending Ethernet packets. So that line goes high when you're blasting stuff out on the network. So when there's nothing, this is a clean network segment now. This shows the jitter standard deviation is 20 nanoseconds. So that's pretty good. That's like one clock cycle, essentially, of the clock that's running the Ethernet transceiver. So, but what we oftentimes care more about in real-time stuff is the worst case. And so that shows we're getting the worst case there is about 200 nanoseconds. So that's great. But again, this is the best case. Nothing else is on the network. So to try to make it more difficult now, my workstation is pinging this poor microcontroller at 8 kilohertz, while it's also trying to give us the accelerometer back at 1 kilohertz. So now when there's more stuff going on, as you'd expect, so there's more cache misses and there's more jitter happening. So now we're showing about a 2 microsecond jitter or so. So this is on a 1 millisecond period, we have 2 microseconds of jitter. So it's about 0.2% jitter. So that's pretty good. So then now if we zoom in now, what we care about oftentimes also is latency. So the yellow trace, remember the yellow trace goes down, we talk to the accelerometer, we get its data back, and then there's a delay while we're crafting our packets and stuff until the green trace goes back up there, and that's actually when we're sending out the RTPS message. So we want that delay to be small and also to be predictable. And so this measurement here shows that after taking 7,000 measurements on the oscilloscope, it says that what happens there is we have about a 34 or 35 microsecond delay, and the jitter is about 2 microseconds. So now, those are the kind of ballpark where we are. We can improve this, of course, over time, but I wanted to just show where things are as it stands. So to summarize, ROS2 with the DDS underneath it and RTPS underneath that is much more embeddable than the ROS1 protocols. It's just much more friendly to these static memory situations of highly memory constrained systems. Going forward, I'd love to attack more microcontrollers, especially small ones. So this is relatively big 32-bit microcontrollers that I'm showing these demos on right now. Oftentimes we want things to get smaller. And ironically, if you'll see these dev boards, the Ethernet connector in its transceiver is actually larger than the microcontroller nowadays. So we don't want that, it'd be great as we shrink things down to use different physical layers than Ethernet. So raw USB, like the full speed, high speed, super speed USB is kind of where things have gone because of, in part, connector size, and the transceivers are built into microcontrollers. That saves some board space. But then there's also a whole other world of unframed serial protocols like RS-45, TTL, all just raw UARTs. There's lots of ways things can communicate, whether that or even over wireless as well. So there's some future areas we're going to go after. So thanks for your time.
Thank you, Morgan. Any questions?
Do you require any original operating system or just bare bones implementation?
So right now this thing just, question is, do we need a real-time operating system beneath FreeArt EPS? And so right now the demos are written, if we go back a few slides, underneath that I have this, what I was calling a minimalist UDP v4 stack. That's really nothing other than shoving the DMA descriptors for the Ethernet transceivers and just having it run. So the answer is we don't require it. You can certainly do that. And many applications would want that for various other scheduling reasons if you're doing more than one thing on the machine. These demos, there's really only one thing happening per demo, whether it's an inertial unit demo or the camera demo or a blinker. So it's just going raw, straight bare metal. But you can certainly put an operating system beneath that.
So I tried using ROS to make the system, and it works fine when there's not many messages going around the system, but when you start putting up a whole robot system, and there's thousands of packets going around, I found the really trying to stop because it's not just a message going to that one, it's all the other UDP packets, everything else going around the network to slow it down, which is going to be just network. How would this help?
Okay, it's a great question. The question is, real-time can be difficult to guarantee when there's a lot of stuff in the system going on, lots of packages, lots of packets. Is that a fair summary? Okay. Yeah, so real-time is a whole can of worms. There's actually going to be a talk about using ROS2 with real-time stuff that Jackie's going to give. And that'll go into more detail on these things. But yeah, I can't sit up here and say because you have your microcontroller has low jitter, the whole thing is hard real-time. That's certainly there's a lot more going on in these systems. Essentially what this is trying to say is that this piece of the system can obey real-time things. Depending on what you're doing on the microcontroller, you can show that you can have good timing on your network packets. Now, whatever else happens beyond that on the network certainly could tear that apart. Okay, so the question is what other physical layers are we going to support, whether that's CAN or EtherCAT? Is that a fair summary? Okay, thank you. So the clarification there was that some physical layers, such as CAN bus or EtherCAT, they can actually have multiple microcontrollers on that same physical bus. So they, rather than talking straight to Ethernet, they might need to talk to each other before one of them starts to relay it to the Ethernet. Is that fair? Okay. So yes, that's certainly on the future work slide. I'm not there yet, clearly, but that I think that it's interesting to look at that case. And I think it's an important use case because oftentimes, like the previous question said, if we're trying to have a particular system or part of the system be hard real time, it's oftentimes you want to partition it, and one way it's easy to partition that is with these other physical layers where microcontroller talking to microcontroller. So that's certainly an area of future work. We're not there yet, but I think it's a very interesting place to go in the future. Thanks. So the question was, what about time synchronization? Where if we have lots of different parts of the system, they each have their own clocks, how can we deal with that? That's certainly an issue. If you look at these traces here, you can see that I'm actually running it slightly faster than 1 kilohertz because of the clock speed differences. That's always the case. Clocks aren't perfect. That's certainly an issue. I think that's somewhat orthogonal to this. I think that time synchronization, whether we're using the Ethernet standard protocols or some other mechanism, whether GPS pulses or something, I think that's certainly something that needs to happen to build large systems, but it's not quite addressed by here. I think that would be another kind of parallel process that's keeping the timing information correct.
I guess this is a little bit kind of aside the point, but I'm just curious, you were mentioning how ROSCon is a pain at startup, because you have to wait for the core and everything. So other startup issues are like how the controllers identify themselves, like would it just all be by MAC address, or would be there some way that this system could help with the kind of self-identification and discovery and kind of overall bring up of the robot?
Right. So the question is about how, when we start up a big robot system, oftentimes we have to deal with lots of different controllers coming up online. Perhaps you have the same motor controller, for example, but you have 20 of them, and they need to tell you which motors belong to which joints. And yeah, I think, like you said, it is a bit of a separate problem to deal with, whether that's a configuration, maybe a different, rather than real-time discovery, we could even hard code some of those things by MAC address to map those to topic types, like you mentioned. I do think it's a bit of a separate issue. This talk is just purely dealing with the transport layer of how can we send messages from one node to another node. Yeah.
One last question before we go to lunch.
You mentioned that you take 100 kilobytes for the IM message. Do you have information on how this breaks down to the various parts of your library?
Okay, sure. So the question was, I threw out the number 100 kilobytes there without explaining it at all or showing any kind of plots there. So yeah, the whole demo takes 100 kilobytes when it is done linking up. Obviously, the IMU messages themselves are like a few tens of bytes, so it's not just message buffering here. So a lot of that, I can certainly talk offline. We can show the linker maps and stuff. A lot of it is just when I called a bare metal UDP stack, there actually has to have a ring buffer and DMA descriptors and places for that to land. That's actually the bulk of it, is dealing with the inbound and outbound Ethernet buffers. Some of it is code buffers that you also need for the discovery, but that actually tends to be smaller. A lot of it is just the Ethernet buffering. So with smaller physical layers, we could definitely drive that down. If we're just doing a sequence of packets on like a UART or a TTL serial line of some sort, odds are the locator is going to be much smaller, the descriptors and identifiers are smaller, everything can shrink down as we go to smaller physical layers.
Let's thank the speaker again.